When we lift our eyes to the night sky, the tiny points of light we see resemble small lanterns, yet behind them lies a universe so vast, so boundless, and so mysterious that humanity has only grazed the surface. The universe is not merely an immense stage on which celestial bodies move. It is a long narrative of formation, evolution, and the fundamental physical laws that govern all existence. From the beginning, the question, where did the universe come from, has haunted the human intellect, and out of the desire to answer it, modern science has erected a majestic yet still enigmatic picture of the universe's origin and operation. According to the Big Bang Theory, first proposed by Georges Lemaitre in 1927, and later reinforced by Edwin Hubble's 1929 observations of cosmic expansion, all space, time, matter, and energy were once compressed into an extremely hot and dense state, then expanded, initiating a continuous enlargement that persists to this day. The most persuasive evidence for this hypothesis is the cosmic microwave background radiation, CMB, discovered by accident in 1965 by Arno Penzias and Robert Wilson, the afterglow from when the universe was only about 380,000 years old. That discovery opened a new era of observational cosmology. Since then, satellites such as COBE 1992, WMAP 2003, and Planck 2013 have provided exquisitely detailed measurements of the universe's primordial structure, allowing us to infer the conditions near the beginning. If we rewind to the Planck moment, about 10⁻43 seconds after the Big Bang, our present physical laws fail us. Under conditions of extraordinarily high temperature and energy density, the four fundamental interactions, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, may have been unified into a single superforce. Theories, such as string theory and loop quantum gravity, seek to describe this regime, but remain, for now, in the realm of theory. Immediately after the Planck era came cosmic inflation, an ultra-rapid burst of expansion within a tiny fraction of a second. This idea, proposed by Alan Guth in 1981, helps explain why today's universe is so uniform on large scales and why its geometry is so nearly flat. After inflation, the universe continued to cool. Elementary particles formed. Then protons and neutrons combined into nuclei in a phase known as primordial nucleosynthesis. About 380,000 years after the Big Bang, when the temperature fell to roughly 3,000 Kelvin, electrons combined with protons to form neutral hydrogen atoms, allowing photons to travel freely and producing the CMB we observe today. From tiny ripples in density at this epoch, and under the inexorable pull of gravity, matter gradually condensed into larger structures, laying the groundwork for the birth of stars, galaxies, eventually, planet. One of the universe's greatest mysteries is the presence of dark matter and dark energy. In the 1970s, astronomer Vera Rubin observed that stars at the outskirts of galaxies rotate far faster than expected from the visible mass alone. This can be explained only if there exists an invisible form of matter that neither emits nor absorbs light, yet contributes the bulk of galactic mass. According to Planck mission results, dark matter accounts for about 27% of the universe's energy budget, whereas ordinary matter contributes only about 5%. The remaining 68% is dark energy, a mysterious component believed to drive the accelerating expansion of the universe, first inferred in 1998 from studies of type Ia supernovae. Since then, dark energy has posed one of modern physics' most formidable challenges, because we still know almost nothing about its true nature. Across billions of years, gravity assembled matter into majestic structures. Stars, forming from the collapse of giant molecular clouds, act as natural nuclear reactors, fusing hydrogen into helium and releasing enormous energy. Over successive stellar generations, heavier elements, carbon, oxygen, iron, were forged, establishing the chemical foundations for life. When massive stars exhaust their fuel, they end in supernova explosions that not only disperse heavy elements into space, but also give rise to extreme phenomena such as neutron stars and black holes. Black holes, especially the supermassive ones at galactic centers, stand as vivid evidence of gravity's unyielding power. In 2019, the Event Horizon Telescope released the first image of a black hole's shadow in galaxy M87, inaugurating a new era in gravitational observation. The universe's mysteries are not confined to grand scales. They reside also in the very nature of its fundamental constituents. The Standard Model of particle physics has succeeded in describing three of the four fundamental forces and in predicting many phenomena with great precision, yet it still refuses to merge with gravity. The 2012 discovery of the Higgs boson at CERN completed the Standard Model in one sense, while simultaneously raising a sharper question. Are there particles beyond the Standard Model that might account for dark matter or other unknowns? Beyond such physical enigmas, the universe provokes profound reflection on life itself. Earth is a small planet in the solar system. The solar system is but one among hundreds of billions of planetary systems in the Milky Way. And the Milky Way is merely one of hundreds of billions of galaxies in the observable cosmos. The probability that life exists only on Earth seems exceedingly small. Missions like Kepler and the James Webb Space Telescope have discovered thousands of exoplanets, many in the so-called habitable zone, where liquid water could persist. The question of extraterrestrial life is no longer merely philosophical. It has become an empirical scientific problem. If life has arisen elsewhere, that fact would transform humanity's conception of its place in the cosmos. When we consider the universe's future, scientists outline several scenarios. If dark energy continues to dominate, the universe will expand forever. Galaxies will drift apart until they vanish from one another's view. Stars will gradually burn out, and a cold, empty cosmos will remain, the big freeze. Some hypotheses suggest that dark energy could change its properties, leading the universe to collapse back on itself in a big crunch, or to tear apart all structures from galaxies down to atoms in a big rip. Each prospect carries an air of mystery, underscoring finitude even for an entity that seems limitless. In humanity's brief sojourn, we have taken only the first steps in exploring the universe. From Galileo's first telescope in 1609 to the James Webb Telescope's ability to peer back more than 13 billion years, human knowledge has pushed outward the boundaries of understanding in unprecedented ways. Yet the more we learn, the more we realize that we are but specks of dust in the vast ocean of space and time. The universe's grandeur and mystery both challenge and inspire us, reminding us that knowledge has no final frontier. The universe is a long scientific epic, a vast stage where matter, energy, and time interweave to produce an endless symphony. We may never grasp the entirety of truth, but every advance, every discovery, every new question testifies to our drive to understand. And in that unending journey, humanity does not merely explore the outer universe. It also discovers itself, a small but self-aware participant in the boundless tapestry of the cosmos.